Hello everybody and welcome back to another video. Today we're going to be looking at one of the most critical scenarios in airline flying, an engine failure after takeoff, also known as an EFATO on the Airbus A350. We'll start with the theory. This will cover the procedure step by step, where trainees often go wrong, and the different types of engine out SIDs. Then we'll jump into the sim with the iniBuilds A350, flying one engine maneuvers including takeoff, approach, landing and even a go around. We'll also cover failure management using option generation models to make right decisions and NITS briefs to keep the crew aligned. Now the simulator does have its limitations, so we've made a few edits and a few assumptions, but the handling, callouts and decision making are true to real Airbus operations. So if you found this video useful, hit subscribe, give it a like, and any questions that you might have, please leave in the comments section down below. Let's dive in.
Welcome to this lesson on the Engine Failure After Takeoff procedure, also known as the EFATO. In this lesson, we will be looking at the following. What is an EFATO? EFATO handling. ECAM handling. Failure management following an EFATO. Considerations when flying a one-engine inoperative approach and landing. A go-around with one engine inoperative. The difference between a standard engine out SID and a non-standard engine out SID. And then finally a practical demonstration. Let's dive in. Following any failure after V1, the takeoff must be continued. An EFATO is an engine failure that occurs after V1. At this point, the takeoff must be continued, and we take the issue up in the air. Causes for an EFATO include bird strikes, icing, maintenance issues, ingestion of foreign object debris. An EFATO creates a high workload situation for many reasons, some of which include controllability issues that it presents, the complex failure management involved, the threat of startle effect to the crew, the proximity to the ground during the event, and the demand for high crew coordination. Let's now look at the handling of an EFATO and the challenges it presents. An EFATO can present a number of challenges when it comes to handling, and where trainees usually struggle is with the following. Maintaining the centerline, their rotation rate, maintaining speed once airborne, following the required track or engine out SID, and centering the beta target. Let's take a deeper dive into each challenge, starting with maintaining the centerline. Crew should look outside, towards the end of the runway, to recognize the drift from the centerline. Then, apply rudder to keep the aircraft straight and hold it there. A slight deviation from the runway centerline is tolerated and often expected in challenging conditions, but never rotate with significant drift or crab angle. So, where are trainees going wrong? They are heads in, so have no visual reference outside. This makes the centerline almost impossible to track. They do not apply enough rudder, or release rudder after application, causing destabilization. They chase the centerline with multiple rudder inputs. Our technique is to hold the rudder, which will reduce workload and keep things stable. Now moving on to another challenge during the EFATO, the rotation rate. The first technique is to look outside to manage the rotation rate. This is your best reference. Your initial pitch is 10 degrees with a rate of 3 degrees per second. This can be achieved by counting in your head. When the visibility is good, you can also use the view of the runway below you to ensure you are keeping track of the centerline. Once you have rotated, follow the SRS. Note that this might be less than 10 degrees, so you will have to reduce the pitch. So where are trainees going wrong? Similar to the previous slide, they are heads in, so have no visual reference outside. As a result, their rotation rate is usually too quick. As this becomes harder to judge, the startle factor causes them to rotate too quickly, or they rotate too slowly, which is also dangerous, as it can affect obstacle clearance. Another challenge is maintaining the speed. With the thrust levers in flex or toga, speed is primarily controlled by the pitch. By following the SRS, you will ensure your speed stays at its target, which is V2 or V2 plus a speed of up to 10 knots. Toga may be selected during an EFATO to increase climb performance, particularly in hot and high conditions. Speed, however, is controlled by pitch, not thrust in this case. Remember that selecting toga will increase your requiring greater rudder input. Where are trainees going wrong? They don't incorporate speed into their scan, meaning that it can often decrease, and they won't even realize. They pitch too high, and then use toga to compensate for speed. This is the incorrect use for toga. They do not follow SRS. Following SRS will mean that you maintain the appropriate speed. So, what are the other challenges? Correctly following the track or engine out SID is also vitally important to do. Maintaining this runway track or engine out SID will keep you safe from obstacles. A good technique here is to ask PM to pull for an appropriate heading or track to follow. The tolerance varies by airline, but is usually 300 meters either side of runway track. In your sim assessments, this is the limit that you will be expected to keep inside. And where are trainees going wrong? Due to incorrect rudder control, they drift outside the tolerances, and they don't compensate selecting toga with enough rudder and drift outside tolerances. The final challenge we will cover today is the centering of the beta target. The beta target is a sideslip indicator displayed on the PFD after an engine failure. It guides the pilot to apply the correct rudder input to cancel sideslip. Centering it ensures you're flying with the least drag, maximizing climb gradient in the critical EFATO segment. During an EFATO, the beta target is shown in blue. If this blue box moves to the left of the triangle, it means you need to apply more left rudder. And if it moves to the right, then more right rudder is required. The goal here is to align the blue box with the yellow triangle, cancelling the sideslip. Once beta target is centered, trim the rudder until no more rudder input is required. So where are trainees going wrong? They do not apply enough rudder, allowing the plane to drift from runway track, and they use the rudder trim to center the beta target. This is not the correct procedure, as you should center the beta target with the rudders, then trim to alleviate any rudder pressure from pilot flying. So now let's take a deep dive into how we handle an EFATO. If our engine fails after V1, we will use the rudder to stop drift and hold that input. Remember to look outside. At VR, PM calls rotate. Rotate at 3 degrees per second. Initially keep looking outside, then bring the scan inside and follow SRS. Call for gear up, and then when capacity permits, ask PM to set the runway track or heading. Continue to follow SRS and keep beta target centered. Follow the runway track and make corrections if necessary to maintain the runway track. Trim the rudder until you don't require any more input on the rudder pedals. Then, engage the autopilot. Note that you shouldn't engage the autopilot if the rudder is not trimmed. Then, once above 400 feet above the airport elevation, call for ECAM actions. Complete the ECAM, confirming the following items: the thrust lever, which is confirmed by pilot flying, the engine master switches, and the fire push buttons, which are confirmed by pilot monitoring. Passing 1,000 feet above airport elevation, pilot monitoring will call engine secure when, if the engine is failed only, then the affected engine master is off. In case of damage, Agent 1 is discharged, and in case of fire, Agent 2 is discharged, or the fire is out. At this point, PF will press the vertical speed to level off, and announce VS0 on the FMA. Once the aircraft is level, you can retract the flaps as you speed up towards green dot speed. Then, as the speed trend arrow reaches green dot, you can pull for open climb. When lever MCT flashes on the FMA, you can set MCT, max continuous thrust. Remember to do this only when you see lever MCT flashing. To set MCT, if you are in flex already, you will need to move the thrust lever to the climb detent first, before moving them back to MCT. If you are in toga thrust, you can move the thrust lever straight to MCT. After that, Continue to follow the SID and complete the ECAM actions. Above 400 feet, and when workload permits, the crew may begin the ECAM actions. Let's look at this more closely. As mentioned before, the thrust lever to idle is actioned by pilot flying, whilst the engine master is switched off by pilot monitoring. Both these items must be confirmed before they are actioned. The next line says, if damage. At this point, the crew should assess if the engine has sustained damage or not. Signs of damage include, but are not limited to, a loud bang, high EGT, N1 at 0, oil pressure is low, or high engine vibration. If the crew notice any of these, they can assume that the engine is damaged, in which case, they should push the fire push button, which is done by pilot monitoring, after they have confirmed it with pilot flying. For management of the failure, we first apply the Airbus Golden Rules. These are aviate, navigate, and communicate. Let's look at these further. For aviate, the priority is stabilizing the flight path. Maintain V2 or V2 plus 10 knots, and trim with the beta target centered. Use smooth control inputs to hold pitch and track, and then engage the autopilot when available to reduce workload. Under navigate, follow the engine out SID, or runway track as briefed. Maintain lateral accuracy within tolerance. Reassess the terrain and obstacle clearance as the situation develops. For communicate, once stabilized, inform ATC of the situation and your intentions. Make an attention, crew at stations. PA, deliver a clear NITS briefing to the cabin crew when time permits, and coordinate with the company if required. Having managed the EFATO and stabilized the aircraft, the next step is the landing. Let's review the key considerations for conducting an approach and landing with one engine inoperative. The crew may choose to fly either an early stabilized or a decelerated profile, depending on conditions and workload. Maintain the slip indicator centered. At high thrust settings, the indication may turn blue, highlighting increased side slip. In such cases, consider delaying gear extension. Rudder trim may be reset later in the approach, but crews should anticipate the increased rudder force required. Note that you can also land without resetting the rudder trim. It comes down to preference. And finally, once landed, crews should select reverse if at least one reverse is inoperative. Do not select reverse if no reverses are operative. A single engine go-around has specific considerations, and it is flown as follows. The call from pilot flying is, go around flaps. Set the thrust lever to toga. Go around soft is not available with one engine inoperative. Apply positive rudder to counter the asymmetric thrust. More rudder is required as we set toga thrust. And center the beta target. Follow the SRS. If it is not available, set 10 degrees. Similar to the EFATO, accurate tracking is essential. Fly the published missed approach as briefed. If performance limits prevent this, coordinate with ATC and state your alternative plan. And then for a one-engine inoperative go-around, your acceleration altitude is your level off altitude. Remember, you are limited to 10 minutes on toga with one engine inoperative. So where are trainees going wrong with this? They do not anticipate the significant yaw and end up chasing the flight directives. Or they over-rotate, or rotate too quickly, not following the SRS, and allowing speed to decrease too much. Before we begin our practical demonstrations, let's have a quick look at non-standard engine out SIDs. So what's the difference between standard and non-standard? A standard engine out SID will vary from company to company. Usually it involves either flying straight ahead, following the runway track, or maintaining runway track. Then once above a certain altitude, engine secure and in clean configuration, making a left or right turn. Meanwhile, a non-standard engine out SID often requires early turns, and in this case, flying the engine out SID takes priority over other EFATO actions. The reason for this is usually to avoid terrain, and this can often involve intercepting VOR radials or turning at specific DMEs. When following a standard engine out SID which takes us straight ahead, a good technique is to create an outbound radial from the runway, which gives us a visual line to track following an engine failure. To do this, on the flight plan page, click the bar at the bottom which says Flight Plan Info, then select Fix Info. This brings up the Fix Info page on the MFD. Here, enter the runway threshold where it says Refident, and then the radial should be the runway track. This will then give you a blue line, which you can track following an engine failure. This technique improves your situational awareness and reduces workload, as you simply have to put your track line over the blue line, and you are following the standard engine out SID.
Runway 36 center, cleared for takeoff, Airbus 123.
Takeoff. Manflex 57, SRS, runway, auto thrust blue.
Checked. Thrust set. "100 knots.
Checked.
V1.
Rotate. Engine failure. Positive climb.
Gear up.
Gear up.
Pull heading. Heading.
Checked.
AP1. Track.
Checked. Pan, Airbus 123 engine failure following runway track. Stand by for intentions.
Read ECAM.
Engine 1 fail. This is confirmed on the engine warning display, as N1, N2 and N3 have all dropped. The overhead panel shows associated fault lights for the failure.
That's checked. ECAM actions.
Thrust lever 1, idle.
Confirm thrust lever 1.
Confirmed.
Idle.
Engine 1 master, off. Confirm engine 1 master?
Confirmed.
It's off. Engine 1 damaged?
N1 and fuel flow are at 0. There was a loud bang and some high vibration. Engine is damaged.
I agree. Engine damaged. Yes. Engine 1 fire push button, push. Confirm engine 1 fire push button?
Confirmed.
It's pushed. After 5 seconds, engine 1, agent 1, discharge. Engine secure.
Stop ECAM. Speed. Out.
Checked.
Set standard.
Standard set. Flight level 36.
Checked. Attention crew at stations. Flap 0.
Speed checked. Flaps 0.
Open climb. Flight level 40 blue. Thrust MCT. Auto thrust.
Checked.
Speed. Out star. Out.
Checked. Fly heading 270, Airbus 123.
Heading.
Checked.
Continue ECAM.
Clear engine 1.
Clear engine 1.
Air abnormal bleed configuration. This is confirmed on the bleed SD page. We can see the whole of the left side is now inoperative.
That's checked.
Avoid icing conditions. Clear bleed.
Clear bleed.
Engine 1 shut down. This is as expected. Land answer. Fuel imbalance monitor. At the moment, we can see there is a slight imbalance forming, so at some point, we may need to perform a fuel balancing ECAM procedure.
That's understood.
Go around thrust, toga only. Landing distance affected. Clear engine 1.
Clear engine 1.
ELEC. On the AC ELEC page, we can see we have lost generators 1A and 1B. Generator 2A and B are supplying the affected bus bars. APU is available.
Let's start the APU.
Starting APU. Clear ELEC.
Clear ELEC.
Bleed. As we saw earlier, the left side of the bleed system is lost. Clear bleed.
Clear bleed.
Hydraulics. We have lost the engine 1 driven pumps for the green and yellow system. Hydraulic power still remains, and the system is powered via the engine 2 hydraulic pumps and the EHAs and EBHAs. Clear hydraulic.
Clear hydraulic.
Status.
Stop ECAM. Fly heading 210, Airbus 123. So there are no normal flows or checklists to consider. No resets, no expanded checklists. Continue status.
Status reads: Info. On dry runway only, landing distance affected less than 15%. Inop systems, Gen 1A and B. Approach and landing. We have lost BTV and go around soft. Alerts impacting landing performance. Engine 1 shut down. Limitations, all phases. APU bleed, do not use. Avoid icing conditions. Remove status.
Remove status.
Status removed. ECAM actions complete.
Okay, so we are flying with automation engaged. On A heading of 210, we are clear of weather, terrain and traffic. ATC have been updated and crew alerted. Let's now move on to a DODA. If you're ready.
Ready.
D. Diagnosis. We have had an engine failure at takeoff, with the engine being damaged. We shut it down and secured it. Options are to continue to roam, return to Amsterdam, or divert to another airport. We have Dusseldorf and Brussels a bit further on. What are your thoughts?
I think Amsterdam is a good option. It is close by and we're familiar with it, has multiple long runways with an ILS with good weather.
I agree. So let's decide on a return to Amsterdam. Before we continue, Let's request to enter a hold near the airport.
Airbus 123, we will be returning to Amsterdam. Request to hold at Papa Alpha Mike, and we will advise when ready for the approach. Hold at Papa Alpha Mike is published. Expect ILS approach runway 18 right, Airbus 123.
So we have decided on Amsterdam and entering a hold at Papa Alpha Mike. Let's move on to A. Assign. A. Assign. I will hand you control. Then I will update the FMS and do a landing performance. I will then take back control and radios from you and will ask you to give the cabin manager a NITS briefing, update the passengers and the company. We will then have a brief where we can review our situation.
That's understood.
Okay, the FMS is updated and the landing performance complete. Now let's bring the cabin manager to the flight deck and we can give her a NITS brief. Senior cabin crew member to the flight deck.
Hi there.
Hey Cheryl, how are you doing?
Doing fine. We heard a loud bang at takeoff and have been sat at a station since you made your PA. The passengers are looking quite anxious.
That's understood. Are you ready to copy a NITS brief?
I'm ready.
Nature of the problem is we've had an engine failure at takeoff. We have secured the engine and are flying fine on the remaining engine. Intentions are to return back to Amsterdam. Time will be 10 to 15 minutes. Expect a precautionary landing. And then once we have landed, you may see some fire services. However, we are expecting to vacate the runway and taxi back to stand. Could you read this back?
Sure. So the nature of problem is we've had an engine failure at takeoff. Engine is secured and we're flying fine with one engine. Intentions are to return back to Amsterdam. This will take 10 to 15 minutes. Expecting a precautionary landing, with fire services to meet us once we have landed. Expecting to taxi back to stand.
Great. Thanks, Cheryl. See you on the ground.
Thanks guys, bye-bye.
Okay, we have completed all assigned tasks and now we just need to brief. Let's tell ATC we are ready for the approach and request an initial vector for runway 18 right.
Roger. Airbus 123, ready for the approach, requesting vectors for the ILS 18 right. Fly heading 040, Airbus 123. Fly heading 340, Airbus 123.
For the brief, the big picture is that we are planning to fly a single-engine ILS approach onto runway 18 right. The final approach point is at 6.1 miles out, with a platform altitude of 2,000 feet. The plan is to fly this approach as decelerated to avoid too much strain on the remaining engine. The go-around procedure turns us right after 500 feet, direct to Alpha Mike 624, then heading 300 after that, maintaining 2,000 feet. Are there any threats you'd like to discuss?
The main thing here is that we're on one engine, so we must take extra care when handling, especially during the landing and the go-around. Also, once we land, our workload will be increased due to liaising with ATC and potentially fire services, whilst also keeping crew and passengers informed. So let's make sure we prioritize, take things slow, and aviate, navigate, communicate at all times.
Sounds good to me.
Fly heading 310, Airbus 123.
Victor Papa Bravo identified. Activate the approach phase, please.
Approach phase activated.
Can you extend the center line, please?
Center line extended. Descend 2,000 feet, QNH 1022, Airbus 123.
VS 800. Set QNH.
QNH cross-checked. Passing 4,100 feet now.
Checked.
Fly heading 260, Airbus 123.
Approach checklist.
Baro ref.
QNH 1022.
QNH 1022. Minimum.
Baro 190 set.
Runway condition.
Wet 5 selected.
Auto brake.
Off.
Approach checklist complete.
Checked.
Fly heading 210, cleared ILS approach runway 18 right, Airbus 123.
GS, Lock Blue, Land 3 dual, AP1 plus 2.
Checked.
Flaps 1.
Speed checked. Flaps 1.
Flaps 2.
Speed checked. Flaps 2. $160 knots until 5 miles. Airbus 123.
Speed selected. Lock star.
Checked.
Lock.
Checked.
Out star.
Checked.
Out. GS star. 2000 set for missed approach. Gear down.
That's checked. Gear down.
GS.
Checked.
Speed managed.
Checked.
Flaps 3.
Speed checked. Flaps 3.
Flaps full.
Speed checked. Flaps full.
Landing checklist.
Landing checklist complete.
Checked.
Runway 18 right. Cleared to land. Airbus 123.
Checked.
$500.
Land.
400.
Autopilot off.
$100 above.
Checked.
Minimum.
Continue.
Checked.
100. 90. 80. 70. 60. 50. 40. 30. 20. Retard. 10. 5.
Spoilers. Reverse green. Decel. $70 knots.
$500. $400.
Going around. Airbus 123.
Go around. Flaps.
Flaps 3.
Mantoga. SRS. NAF.
Checked. Positive climb.
Gear up.
Gear up.
Out.
Checked.
Flaps 1.
Speed checked. Flaps 1.
Flaps 0.
Speed checked. Flaps 0.
Speed.
Checked.
AP1.
Checked.